Now we're going to take a closer look at those normal distributions. So most statistics gathered in the natural world tend to have a normal distribution with a symmetric bell curve centered on the mean. All normal curves have the following properties, sometimes called the 68, 95, 99.7 rule or empirical rule. And that says that 68% of our data will fall within one standard deviation of the mean. Remember, we talked about standard deviation is the average distance every data is away from the mean. So we can also use it in other ways to measure. So in a normal distribution, 68% of my data should fall within one standard deviation above and below of the mean. 95% of my data will fall within two standard deviations of the mean, and 99.7% of the data will fall within three standard deviations of the mean. You can see to the right, it illustrated there for you. In the center, we do have the mean. This is a different symbol than we talked about in our last lesson. And this is the Greek symbol used to represent population mean. So don't let that confuse you. And you can see 68% of our data is going to fall to the left, our population mean minus one standard deviation. And to the right, our population mean plus one standard deviation. As you move outward, we also see the 95% of the data is going to fall mean minus two standard deviations, mean plus two standard deviations. And then, of course, the 99.7%, most of our data is going to fall between our mean minus three standard deviations and the mean plus three standard deviations. I added an additional image below that because you'll be asked about like what percentage of the data falls between. Obviously, if you take 68% and you cut it in half here, you have 34 and 34%. If we keep moving out towards that 95%, as we add that, we'll have 13.5% on each side there. The next little segment is 2.35%. And so we talked about up here 99.7%. There's still a tiny little bit that doesn't fall in. And so on each side, we have 0.15 of a percent, very, very small majority that falls outside of three standard deviations below and above. So just some values there for you to reference as you answer questions. So let's look at some examples. Number one, in an all-boys school, the heights of the student body are normally distributed with a mean of 71 inches and a standard deviation of 4.5 inches. Use the empirical rule, that 68, 95, 99.7 rule. Determine the interval of heights that represent the middle 95% of the male heights from this school. So 95% means that we are above or below two standard deviations from the population mean. So if my mean was 71, let's subtract two standard deviations. They said was 4.5. Just going to show it this way. Subtracting it twice is going to give me the lower side, and then 71 plus two standard deviations is going to give me the higher side. And so my mean is 71. Just going to use this image here. We're looking for that middle 95% here, two standard deviations below and two standard deviations above. So 71 minus the 4.5 minus another standard deviation, 4.5. My low end is going to be 62. And then 71 plus 4.5 and another standard deviation, 4.5. My upper side is going to be 80. So 62 to 80. So to write that interval, you are going to use parentheses 62, 80 to represent that 95% of the average heights at this all-boys school. Number two, Ryan runs the 400-meter dash. His finishing times are normally distributed with a mean of 75 seconds, a standard deviation of 0.5 seconds. Use the empirical rule to determine the interval times that represent the middle 68% of his finishing time for the 400-meter race. 68% is when I have plus or minus one standard deviation. They said his mean was 75. We're going to go out down one standard deviation and above one standard deviation to show that 68% of the data. his mean was 75. Let's add 0.5, and we're also going to subtract 0.5 to give me the upper and the lower. We have 75.5 as his upper interval, and then 74.5. So to show that, we have 74.5, comma 75.5 would represent Ryan's 68% of his finishing times. Number 3, IQ scores are normally distributed with a mean of 100, a standard deviation of 15. Using the empirical rule, what percentage of people, is it 68, 95, or 99.5% of people that have an IQ score between 55 and 145? All right, so we've already been told that the mean, the population mean, was 100. I like to kind of draw this out. And let's check. Let's subtract one standard deviation and add one standard deviation. Let's see if it's 68%. So I'm going to do 100 minus 15 as the standard deviation and 100 plus 15. So we're going to have 85 on the lower side, 115. Have we made it? Not yet. So let's keep adding standard deviations. So let's subtract 15 on the lower side. 85 minus 15 gives us 70. Adding 15 for this upper side, the 115 plus 15 is 130. Still not quite there, but I think we're going to get it if we add the 3, or we're 3 standard deviations away. So let's add 15 and subtract 15. So 70 minus the 15 is 55. Good. And then 130 plus 15 is 145. Perfect. So we finally found those values, just adding or subtracting standard deviations away. We are 3 standard deviations away on each side. So this is going to be 99.7%. We did plus or minus 3 standard deviations, 99.7%. Number 4, at a local restaurant, the amount of time that customers have to wait for their food is normally distributed with a mean of 26 minutes and a standard deviation of 5 minutes. Using the empirical rule, what percentage of customers have to wait between 21 minutes and 31 minutes? So they told us our population mean was 26. Let's add 1 standard deviation and subtract 1 standard deviation from each side and see. Standard deviation is 5, so subtracting 5 on the left side. Lower in 21. Hey. Adding 5 on the other side. We do get 31. We did not have to go very far. So we are 1 standard deviation above and below. We added and subtracted 1 standard deviation. So the final answer, 68% of our data is represented by individuals that have to wait between 21 and 31 minutes for their food at the restaurant. In our next example, we have Ella and Alicia are comparing their scores for their college entrance exams. Now, Ella's SAT score is 1380. Alicia's ACT score is 32. So if you're just looking at the numbers, these look way different, right? Because they're 2 different tests. So we have SAT and ACT. The mean SAT score is 1,000 with a standard deviation of 200. The mean ACT score is 21 with a standard deviation of 5. So let's just look here. We had Ella's 1380, and that is what is represented right here. This is Ella's score, 1380. And then we had Alicia's score was a 32, and that is shown right here. They also indicated in these images those means. So the SAT mean score was the 1,000 population mean. ACT was a 21. So those are those center lines that you see there. They've also indicated Ella's score is less than 2 standard deviations. Like you can see those little lightly shown lines there. Those are the standard deviations. Ella is just slightly to the left of that second standard deviation line. Alicia is more than the 2 standard deviations. You've got those 2 faint lines for those standard deviations, and she is to the right of it. She's above 2 standard deviations. Now, most data values are not an exact integer number of standard deviations away from the mean, like we're seeing here. Like the girls are not right on the money. So we use what's called a z-score to calculate fractional standard deviations above or below the mean. So on page 1, we were working with 1 standard deviation, 2 standard deviations, or 3 standard deviations away. What this is saying is it's not always just 1, 2, or 3. It is going to possibly, in real life, be a fractional standard deviation away. So that's kind of what we're seeing here with Ella and Alicia's score. To find the z-score, it is your data value minus your mean over standard deviation. I have a slight typo there. So we have our data value x minus the population mean over standard deviation. And just so you know, this formula for z-score is on your EOC reference sheet. So we are going to calculate Ella and Alicia's z-score to determine who truly has a better score. We're trying to compare apples and oranges right now. We kind of need to put them on the same playing field so we can truly compare who did better. And so that's what the z-score is going to help us do. So for Ella's z-score, I've got it represented z sub e, e for Ella. We've got to do our data value, which was Ella's score, the 1380, minus the mean, I wrote it here, 1,000, all divided by the standard deviation was 200. All right, grabbing the calculator really quick, we're going to put this in the 1380 minus 1,000 over the 200, enter. 19 over 10, let's change it to a decimal. Menu, number, convert to a decimal. 1.9 is Ella's z-score. Alicia's z-score, I've got it noted as z sub A for Alicia. She's got her score 32 minus the mean of 21 over standard deviation of 5. Let's grab the calculator. Using that control divide to give me those fraction boxes, 32 minus 21 over the 5. Enter. 11 over 5, let's change it to a decimal. Menu, number, decimal. 2.2. All right, who did better? So Ella's was the 1.9. Alicia was a 2.2 z-score. Who did better? Alicia scored better. Now, do be careful. Always remember your context in your word problems. A positive z-score is not always better than a negative, or a higher z-score is not always better than a lower. Be careful to consider the context. So think about, what if this was a golf game? What if they were playing golf? If you're not familiar with golf, a lower score is better. So always think about that. I'm also going to write here, a higher z-score is not always better than a lower one. Okay. And for the last part of our notes, we're going to talk about percentile. So a percentile of a particular data value is equal to the area to the left of that data value under the distribution curve for the population. So imagine a normal distribution curve, like wherever the score is, everything to the left of it, that population would give you your percentile. So let's compare Ella and Alicia's percentiles. See how they scored in comparison to the rest of the population that took the test. We know that Ella's z-score was the 1.9, just copying it from above, and Alicia's z-score was the 2.2. Let's grab the calculator. All right, on our calculator, we just need to be on a calculator page, which we already are. I'm going to go to menu. Statistics is number 6 there. Number 5, distributions. And number 2 there is normal CDF. Now it's going to already populate your lower bound, and we are going to leave it as such. That is negative 9 times 10 to the 999 power. It's as small as possible, all the way to the left. We want to keep that because remember, percentile is all the values to the left of the curve. So hit tab, and we are going to put in our upper bound. Let's do Ella's first, the 1.9. Tab, and OK. The only thing we entered was the upper bound for Ella's score, 1.9. Hit enter, and there we have 0.97. Let's just round it to the hundredths. 0.97 or 97% is Ella's percentile. Let's do it again for Alicia. Again, we went from menu, statistics, distributions, and then the normal CDF number 2. Leaving the lower bound as such, Alicia's z-score was 2.2. tab to OK. And we have 0.98. Oh my goodness. Oh wait, 0.986. So that really should be rounded up. 99 percentile. Wow, Alicia scored really well. Really well. Let's fill in our blanks here. For Ella, this means Ella scored better than 97% of the other test takers. And for Alicia, she scored better than 99% of the other test takers. So in this lesson, we dove a little bit deeper into the normal distribution, starting with the empirical rule. Guys, the empirical rule is also on your EOC reference sheet. So memorize it if you wish, but you will have that available to you, the 98%, 95, and 99.7%, and that is 1, 2, and 3 standard deviations away, is available on your reference sheet. We worked a couple problems using that, whether that was finding the intervals for a percentage or vice versa. They gave us the interval and we found the percentage based on the empirical rule. On page 2, we dove into the z-score and noticing that in a real world scenario, we're not going to have 1, 2, or 3 standard deviations away from the mean. It's going to be fractional. And so that's why we have the z-score to give us a little bit of a precise measurement away from our mean. It is our data value minus the mean divided by standard deviation, which is also on your EOC reference sheet for you when you take your end of course test. And then the last part, we found percentiles to really see the percentage that we scored above the rest of our population, which we used our calculator, which was so easy. We just put in our data value and the rest was already set, and we got those really quickly. So let me know if you have questions, guys. I kind of love this, diving a little bit deeper into the statistics behind our normal distribution. I hope you do too. I'll see you in class. Have a great day.